Hello, everybody. Welcome to the Extragalactic Astronomy session. This is going to be a session which features 5 talks by our speakers. My name is Rebecca Hounsell. I'm going to be your session chair. The first talk that we have today will be given by Michael Fausnaugh. And if you have questions, I just remind you to please leave your questions in the Extragalactic Astronomy chat channel in Slack, and we'll get to them at the end. This talk's going to be 20 minutes long with 5 minutes for questions, which I will give a warning of as we progress. And so for now, let's please hand it over to Michael. Thank you very much.
All right, thank you, Rebecca. I think we'll do the obligatory and check on the audio. Can you hear everything?
Yes, sounds good.
Cool, thank you. All right, well, thank you for coming. The title of this talk is Blips, Bursts, and Booms. So I've just tried to map each of those onto a different area of astrophysics. The blips are galactic transients, the bursts are active galactic nuclei and supermassive black hole environments generally, and the booms are supernovae. And I'm going to try to give you some sense of what TESS has been contributing to these fields in the last 3 years since it's been operating. But it is a lot of ground to cover, so we're going to dive right in. First things first, I just want to give you some sense of what the state of the art in observational transient astronomy is like. And to do that, I have this table and this figure, which roughly track the activity in this field by reporting the total number of supernova discoveries per year over the last 10 or 20 years. And what you can see is looking at the plot, this really rapid growth in the rate at which supernovae are being discovered since 2011. So this is largely driven by technology. It's really in the last 10 years that astronomers have focused on building and bringing online dedicated ground-based transient surveys. So surveys where 100% of the telescope or instrument time is dedicated to finding transients, or at least a large fraction of the time on the telescope is doing that. The other major technological advance is in automation. So all of these surveys are, so I've listed some of the preeminent surveys on the slide, and they're all run robotically. So that leads to more efficient use of resources, more efficient observing, and generally more of the skies being covered every night because of this. So looking, for example, between 2014 and 2016, really rapid growth in the rate at which supernovae discovered that had everything to do with the fact that you've got these 3 transient surveys coming online and starting operations right around that time. Okay, so dedicated, automated, ground-based transient surveys. There's actually a lot of them operating right now. There's a wide diversity of surveys, different sorts of science cases, different observing strategies. Just to give you some sense, I've posted some telescopes and cameras and enclosures and detectors from the different surveys at the top. And below that, a comparison of the field of view of some detectors being used in transient astronomy, either currently or about to come online. Just like any survey, you've got to make choices in how the observing pattern is going to go. There are trade-offs and choices you need to make in, say, the depth or the cadence or the solid angle of your survey. That'll, of course, will flow directly from the science cases you're interested on. But overall, I would say this is a pretty good thing for the field, since it means we have multiple windows open on the transient universe. We can see the same sorts of objects from different perspectives based on these different surveys. And we also have the opportunity to see different kinds of transient phenomena, depending on what survey specifically you're looking at. But I think that diversity in surveys also underscores the point that there's no single survey that can do everything that you might be interested in as an astronomer working in transient astrophysics. And that's the context in which I want to bring TESS into the picture. The reason being is that TESS, of course, has these very unique data capabilities. There's no other facility on the ground or in space that can do quite what TESS does. And what we've seen in the last 3 years are transient astronomers using TESS data to augment and expand the science and the investigations that they're doing with their ground-based surveys. So I've tried to distill what I think are the key aspects that TESS brings to bear for transient astronomy, and put them in these primary color badges. So I would say it's the continuous coverage, the large field of view for TESS, and the very rapid cadence. And what I'll do as we discuss individual results is I'll bring these badges back just as a kind of reminder of what it is that TESS has kind of uniquely brought to the table that enables these new scientific investigations. Okay, so then I'm going to jump into discussing some of these individual results. Again, we're going to cover 3 fields of astrophysics, the blips, the bursts, and the booms. And I am going to start with blips, so galactic transients. And more specifically, I'm going to focus on the more exotic kind of galactic transients, compact objects in binary systems. So if you've got a binary system, one of the members is a white dwarf or a neutron star or a black hole. It's actively accreting material from a companion star, probably a main sequence star, maybe a giant star. These are sort of mainstays in transient astronomy. These systems are subject to all kinds of instabilities and outbursts and explosions. They show up really clearly in ground-based surveys, and they're rare enough that many of these surveys have science cases focused very specifically on these kinds of objects. So the first use case for TESS data is as a kind of archival data set. And this is enabled by TESS's very, very large field of view and the fact that it's very nearly an all-sky survey. The idea being that if you detect a transient with some telescope or detector, you can check if TESS has observed that field of view either in the past or is scheduled to at some point in the future, go look for a light curve and see if you can get additional data in that way. So I have 3 examples of that on this slide. There was this nova from March of 2018, a new cataclysmic variable discovered in outburst last fall. So this is an accreting white dwarf system, and a new black hole X-ray binary discovered from an outburst in April of this year. In all cases, TESS observed the fields of view of these objects within about a year of when the transient occurred. The researchers went back and extracted TESS light curves, and specifically they're looking for periodicities with the hope that you can constrain the orbital period of these systems. As you might expect for a binary system, getting the orbital period is a key component of figuring out what's really going on with them. And so here's an example of that for the nova. This is the TESS light curve taken about 400 days after the event. So that's sort of the first use case for TESS data. I did want to spend just a little more time talking about this nova in particular. So again, TESS missed the transient, but the researchers do have this very high signal to noise, high cadence optical light curve, which you're seeing in the top panel here. They could correlate that with the gamma ray light curve and constrain where the gamma ray emission is originating in this nova outburst. And it turns out the answer is in shocks, mostly in shocks in material surrounding the white dwarf. And if you follow the energetics, in fact, a very high fraction of the luminosity is thought to arise in these shocks based on this object, something like even up to 50% of the luminosity of the nova. So that's a really surprising result and kind of at odds with the classical picture of how nova work, which has more to do with the accretion disk and explosions on the surface of the white dwarf. I mentioned this not so much to talk about the details of nova physics, so much as to say this very high cadence, high signal to noise optical light curve is exactly the kind of thing that TESS was designed to do and should be able to do, and in fact frequently does do for transients. So one thing I've been doing at MIT is keeping track of transients reported to the IAU and checking if they land in the TESS fields of view. If they do, I extract FFI light curves and I post plots of those public facing URL. So you're very welcome to go to the URL and skim through these plots and see if there's anything that you find interesting. I'm always happy to collaborate. Feel free to send me an email if you do find something. But the main point is just that looking very quickly through the database, I found no fewer than 12 of these nova cataclysmic variable outbursts. In fact, there's many more up on the database. Very high signal to noise in some cases. And it just shows you it's just a matter of time before we can, eventually we'll have an object that we have multi-wavelength data and this kind of cross-correlating exercise. We can look very deeply into the physics of these compact accretors. Okay, I'm going to move on to the bursts, so activity near supermassive black holes. We're actually going to hear a lot about these and the different uses of TESS later in the session, so I won't spend time reviewing those results. Instead, I'm going to try to fill in what TESS is being used for in the space for some other cases. And I think the place to start with that will be with blazars. So blazars are this class of object. They have this reputation as being really messy, really difficult to interpret. There's a lot of conflicting conclusions and analysis and even data in the literature for these objects. What we do know for certain is that they're supermassive black holes rapidly accreting through an accretion disk. They launch relativistic jets, and if those jets are pointed back towards the Earth or the observer, or in our case TESS, relativistic beaming effects come into play, and you'll have something that we canonically call a blazar. They have broadband spectral energy distributions from the radio to the X-rays and gamma rays, and very rapid timescale variability on timescales of minutes, and also on longer timescales, years and even decades. Putting all of that together and understanding the specific components of the blazar SEDs and the origin of all this optical variability is a pretty big mystery. Some of the other open questions surrounding blazars are what are the source of the seed photons that are upscattered by inverse Compton to X-rays and gamma rays? What are the physics of the jet? How is the jet launched? How does the jet evolve? Is there substructure in the jet? Are there magnetic fields in the jet? And if so, how are they oriented? How are high relativistic populations of particles accelerated to high energies, and so forth? And like I said, there just hasn't been a clear picture of how all of these things fit together in blazars. So in fall of last year, there was this paper by Weaver et al. This is work coming out of the Boston University Blazar group. They were looking specifically at the archetypal blazar BL-LAC, and they have this really phenomenal data set from radio waves through the optical, ultraviolet, and then high energy light curves as well. And they also have them all simultaneously and at very, very rapid cadence. And I mentioned this paper not so much because it answers a lot of questions about jet physics in blazars, but because they arrive at this key conclusion that a lot of the ambiguity in past blazar studies has to do with gaps in the data and lower signal to noise data. This has just made it really hard to interpret what's concretely going on. And this is really clear if you compare what they did with TESS light. This is a 2-minute light curve at the bottom here. Compare that with a ground-based optical light curve. So this is actually an exquisite light curve as far as it goes for blazars. There's many telescopes that are intercalibrated to very nice precision. It's actually very high signal to noise, at least as you get from the ground. But there's just a comparison with the TESS data at 2 minutes at this high signal to noise. There's all sorts of substructure and flares that you would miss if you were only using ground-based data. That sort of drives their main conclusion that a key aspect for advancing blazar science is going to be continuous coverage, and TESS is kind of the preeminent facility for doing this right now. Driving this point home, here are 2 more papers studying different blazars using TESS published in just the last 4 months. You can see the TESS light curves, these tight clusters of black compared to the optical data, which is more spread out, more gappy, noisier, or the TESS data in blue compared to the gamma ray light curves. Again, this is just to highlight what a step forward or what an advanced TESS really is for observing these kinds of objects. Okay, the other kinds of transients I'm going to discuss in relation to supermassive black holes are tidal disruption events. So these are cases where a black hole falls close to a supermassive black hole and gets ripped apart by tidal forces. Some fraction of that material remains bound to the black hole and starts accreting and can extract a lot of energy from the system in this way and drive a luminous transient. Tidal disruption events are pretty rare, but TESS did actually observe one in 2019. This has something to do with TESS's large field of view, which increases the probability of observing rare events. But more important for the science in this case is the continuous coverage again, which allows, so normally a transient would be discovered after the star's been shredded as the light curve is rising somewhere over here. But since TESS is always observing, it was possible to follow the light curve all the way back down to before the transient actually started. So they're actually getting first light from a tidal disruption event just as it first approaches the black hole and gets ripped apart. And there's some very novel analysis in this paper looking at, for example, the temperature evolution as the star gets ripped apart, trying to figure out is the bulk of the luminosity coming out in shocks or from accretion processes and so forth. Okay, and next, rounding out these areas of astrophysics are the booms, the supernova. So I think this is probably the easiest science case to understand. The key thing that TESS gives you, it's actually very similar to that tidal disruption event. What you really need for supernova is observing the star right at the moment that it explodes. And again, that's usually not possible from the ground because you would have discovered the transient after the fact. If you can get that observation, if you can get the light curve with the moment of first light of the supernova, there's a huge amount of information you can learn about the system. I've got a list of some of the things you can do on the left, but for the purposes of this talk, I'm going to focus in more specifically on this last point, which is what sorts of companion stars do stars that have supernova, that stars that go supernova have? And even more specifically, what are the companion stars for type 1a supernova? So type 1As are thermonuclear explosions of white dwarfs. The white dwarfs are certainly in binary stars because otherwise you can't disrupt the white dwarf and get it to explode. But there is very, very fierce debate in the literature about what sorts of companions we would expect to see with those white dwarfs that trigger the explosion. The first model is called the single degenerate model, in which the white dwarf is paired with a main sequence companion. The white dwarf accretes material from the companion, it reaches a critical mass and then explodes. The competing model is the double degenerate scenario, in which you have two white dwarfs which merge after inspiraling from gravitational wave radiation. The combined mass of the white dwarf is again over a critical mass, and then the white dwarfs might explode in that way. TESS helps figure this out because when you have these very early time light curves, you can potentially see interactions of a companion star with the supernova ejecta itself. So most of this comes from a sort of seminal paper by Daniel Casson in 2010. The idea is that if you have the companion star represented by this blue blob and expanding represented by this kind of yellow blob, as the supernova collides with the companion star, it reshocks the material, and an observer seeing that shock downstream from the companion will see a little flux excess in the very early times of the light curve, right around the moment of first light. And so if you go find a supernova light curve, you can look for little bumps and wiggles that might correspond to these companion supernova ejecta interaction models, and thereby put some constraints on any companion stars that exist in the system. That's just what they did for this supernova, which is actually very unusual in other ways, but it just gives you a sense looking at this light curve, right? We're just looking for little bumps and wiggles that might be able to tie to these companions. So far, we've published supernova from the first, type 1a supernova from the first 6 months of TESS data. There were about 24 for which that we presented. What you're seeing here are the brightest of those, and these are the ones with the highest signal to noise that we can put the best limits on companion stars. So I should say we didn't detect any evidence of these little bumps or wiggles. So there's no solid detections of a companion. That means that we can only report upper limits, but again, the experiment is you have this nice upper limits before the star explodes, and then you see it as it rises just at the very beginning, right when the star explodes. Our limits come from 6 supernova with the very best light curves. I think they were all in the plot I showed you before. The limits, our claim is that there can be no companions greater than 32 times the radius of the sun in that sample. And actually two of those limits are very, very tight, just a few times the hour of the sun for 2 objects. Now, there is a major caveat, which I mentioned. Part of this depends on the orientation of the observer. The observer really needs to see the shock downstream of the companion star, and random orientation effects means that that will be blocked some fraction of the time. And in fact, with only 6 supernova, even if they all had fairly large single degenerate companions, or they were all single degenerate systems, there's a 50% chance that we just wouldn't have detected anything anyway from random geometric effects. That means that if you want to really constrain single degenerate models, you need a very large sample of supernova. And just to give you a sense of the numbers, you can put a 1%, there's a 1% chance of no detection once you have 30 supernova, assuming that these things were very common. So we're very optimistic that we'll be able to do this relatively soon. Here's the sample from TESS years 1 through 3 of all the supernova TESS observed on the sky. And below that, the type 1a supernova specifically, with the peak magnitude as a function of distance from the Earth. The supernova that you can put these constraints on are in this top left corner, stuff that's very bright, so you have good signal to noise, and stuff that's near to the Earth, because the amplitudes of these little companion signatures are very, very small, and so you need systems that are close to Earth. So far I can say in this box there are 18 that we can put these good limits on. And as TESS observes, we're just going to get more and more supernova. We should either be able to put very good constraints, probably the strongest constraints, on the appearance of single degenerate systems, or we'll detect a single degenerate system, and that would be very big news if it happens. Okay, so that's it for the details of the results that I'm going to show to you. In a review talk like this, there's a lot of results that I just don't have time to go to in any depth, but just to give you some sense of the sorts of things that I ended up passing over. There's certainly more blips. So for example, studies looking specifically at accretion physics in compact binaries. I wanted to highlight this paper in particular that was looking at this magnetized white dwarf and the way the accretion flow changes between TESS year 1 observations, TESS year 3 observations. For the bursts, active galactic nuclei, we're going to hear a lot about that in the upcoming talks in this session. And for the booms, you'll hear about the other kind of supernovae, core collapse supernovae, in the next talk by Patrick Vallely. But it's worth mentioning TESS also observed a gamma ray burst, and there are unique things TESS can do with the gamma ray burst. Again, with continuous coverage, you can times of optical counterparts of gamma ray bursts. We actually know TESS has observed at least 2 more, and that's owing to its large field of view, and we suspect it's probably seen even more than that. And there are actually a couple of undergraduate students at MIT working on exactly this problem. And the last thing I'll mention is this very recent paper, I think just from a few months ago, calculating the rate at which TESS should observe lens supernova in the continuous viewing zone. Lens supernova are important because they allow you to test cosmological models. And in fact, one of the conclusions of this paper is that the rate at which TESS is expected to find these is competitive with projects and surveys that are more or less, maybe not focused on this, but that are very interested in finding those. And if TESS is competitive just by carrying out its normal mission operations, that's certainly a significant finding. Okay, so that brings me into the last stretch of this talk, which is a little more future facing. And I thought in this context, it might be interesting to turn this question around. So what is TESS bringing to the transient surveys and transient science, and how it's inventing that? Just turn that around and ask, so if TESS was to find its own transients, what would they look like and what could you do with them? So we've been thinking a bit about this when it comes to TESS's large field of view. I already mentioned there's the discovery space for very rare events, just because you're surveying so much of the sky. But we've been thinking specifically about LIGO error ellipses, which are of course gigantic. And here's example. Here are all the LIGO events and their error ellipses on the sky. A huge amount of observational resources go into following up these error ellipses and trying to find electromagnetic counterparts. But in principle, if one of these overlapped with a TESS sector, and there's a reasonable probability of that happening because both are so large, you'd have a really efficient way of just searching everything at once if you could do a blind search of TESS FFIs and potentially find those electromagnetic counterparts. Something similar is certainly true with any transient alert that's got poor angular resolution. So for example, neutrino alerts from IceCube or some gamma ray events reported by Fermi. The other place TESS can really shine is in short time scale events, so things that take place on 12 hours or less. And that's just because of the diurnal cycle. It's going to be really hard to get surveys that take place over, to find events that take place between a night. There are some surveys that are beating this time scale, either by observing fields multiple times a night or using networks of telescopes, but still this will depend crucially on the sampling of those strategies. Whereas with TESS, when you have continuous coverage, in principle, something varying very quickly, you should be able to pull these out very easily. So we've been building a pipeline to do just this, a blind search and TESS FFIs for transients. This is work being led by a grad student at MIT, Rahul Jayaraman. We actually do have some candidates for transients unique to TESS. That is to say, here are 3 examples. These were not reported to the IAU as transients. As far as we can tell, the ground-based surveys didn't trigger on them specifically, although there are different reasons that that might not happen. But this is just a kind of proof of concept that there are variables or transient events out there that TESS can find independently. And in particular, that last one, the blue one at the bottom, it's a pretty short duration event, just a couple of days, and that's starting to push into that parameter space where TESS could potentially really shine as a transient discovery engine. In the past, a major difficulty for using TESS as a
interruptions. You're entering into your question time. That's
yeah. We're very close. A major limitation was the data latency. So you could only get the data 2 months after observations in the primary mission. And that's so late that there's probably not much follow-up you could do, and therefore science to investigate on any transients you would find in the FFIs. That situation's helped a bit since Sector 30 with the TICA high-level science products. So raw or calibrated FFIs delivered to MAST just a couple days after sectors finish. That drops the latency to about 14 days on average, which is certainly better, but still pretty slow for this sort of science. But looking forward to the extended mission, if it were to change to downlinks every 7 days and data released on a rolling basis on a similar cadence, that's certainly enough time to be able to coordinate some kind of follow-up programs and get more information about these, what we would hope would be rare and exotic transients. Okay, and that is all I have. So this is the last slide. It's just a quick roadmap of where we've been through the the different areas in astrophysics and some of the highlights of the results that TESS has been able to contribute to. But again, the thing that ties us all together are these unique capabilities that TESS has as an observatory. And I would say that there's no reason to think that the rate at which TESS can contribute to these things is going to slow down anytime soon. And I will leave it at that. Thanks.
Thank you very much, Michael. That was a very interesting talk. We have maybe a minute or so for any questions. If you do have a question, please enter it into the chat and I will read them out. If you have questions after that we don't get to, hopefully Michael can respond through the chat to answer those questions. And sorry for interrupting you there, Michael. I was just trying to make sure we could answer anything that came up now.
Yeah.
Okay, well, it seems that we don't have any questions currently in the Extragalactic Astronomy chat room. Just a note there, that's where you should be posting things. Oh, we do have one from Dan Hubber. How many LIGO events would be expected to be bright enough to catch the EM counterpart with TESS?
So I would assume you're talking about kilonova, since we would have some handle on the electromagnetic brightness of those. We have no idea if there are electromagnetic counterparts for many of the LIGO sources. I do not know this number off the top of my head. So the event from 2017 was very favorable and very close by and has exquisite data. TESS would have really done a great job with that. But they are quite rare, and in many cases, we probably would have sort of lower signal to noise data, but anything we could take would be, I think, super useful, especially considering all the observational resources going into follow-up of those.
Okay, well, thank you very much. Again, if you have any more questions, please enter them into the Extragalactic Astronomy Slack channel. The next talk we have is going to be given by Patrick Vallely. This is studying core collapse supernovae with TESS. Patrick, I believe that you're online, is that correct? But I have your talk that I can play for you if you wish.
Yeah, if we could do that, that'd be great. I just don't super trust my internet connection.
That's absolutely fine. I'll share my screen now. Okay, can everybody see the screen?
Yep, we can see it.
Okay, thank you.
All right. Answer any questions. I just wanted to go ahead and record this in case I had any technical issues because my internet's been a bit spotty over the last few weeks. So my name is Patrick Vallely. I'm a PhD candidate at Ohio State. Today we'll be talking about some of the work I did recently using TESS data from the TESS Prime mission to study core collapse supernovae. So if you're not a supernova person, you've probably heard more about type 1a supernovae. These are the ones that are standard candles and are used for cosmology all the time. But today I'm going to be talking instead about core collapse supernovae. And in a lot of ways, they're actually more important than type 1a's, at least as long as you're not a cosmologist, they're probably more important to the science you're doing. They're certainly more important in terms of nucleosynthesis for elements used to form planets. They're certainly more important for driving the environments around planets. So they're also significantly more common. We see more type 1a's in our samples, but that's just because they're brighter. If you look at a galaxy like the Milky Way over time, you're going to see 3 times as many core collapse supernovae as you will type 1a's. Like I mentioned, they create a really wide range of elements. You can see on this periodic table here, everything in green has an appreciable fraction of their formation we expect to come from core collapse supernovae. So everything from oxygen, sodium, up through krypton and rubidium have significant contributions. So the detailed physics of how core collapse supernovae actually explode is still very much of a question. Once you have material infalling and you get it to bounce off the core, how you actually sustain that and get a supernova shock out of it is very much still a work in progress among supernova theorists. But we know for sure that core collapse supernovae are the result of the death of massive stars. In part, this is sort of a necessary thing in our understanding of the theory and our stellar evolution models. But also, we're able to detect it directly in a lot of cases. Well, in some cases, in the situation where you're fortunate enough to have HST data or something, of comparable resolution, and the supernova was nearby, you can actually go back and look and see, oh, look, there was a red supergiant, or in the case of 1987A, I think it was a blue supergiant, which is great. it's nice to have that kind of data, but it's difficult to get it, systematically. It's tough to do population studies like this just because it's so sporadic. In principle, having TESS light curves lets us back out some properties of the progenitors in a more indirect manner, but in a more systematic manner, which is great and an exciting science case. But in order to do that, you have to actually work your way through the TESS data. So I don't think I need to spend too much time on this. I know everyone here, I'm sure, is familiar with a lot of the issues you have with TESS. We've all, at least anyone who's an observer on the TESS framework, on the TESS side of things, has been, spending the last few years dealing with things like scattered light artifacts, the adventures of momentum dumps, and all the standard issues with the observer, or the standard, challenges raised by the observing system. But at least for us, one of the problems we ran into at the start is that, TESS is a really well-supported mission. There's a ton of awesome publicly available tools, but not a lot of them, especially at the start, were very keyed in for what we needed out of transient science. They were built for looking for these short duration dips on really bright sources and trying to trend out pretty much everything else, which for us, we're looking for these, by the standards of exoplanets at least, long duration signals. So what we ended up doing was trying to build our own pipeline based on what we use at Assassin, an image abstraction pipeline, to try to process the data and get transient light curves out. You can see here, this sort of shows the process we ended up settling on. The most important feature we added on top of the standard image abstraction we do is this round of median filtering, which ended up being really important because the standard image abstraction, it includes this background polynomial feature, but usually when we use that, there was still leftover structure. You can see in this panel up top, you got these amorphous things from the scattered light, but you also have these obvious striations. These are the CCD background straps. So we're able to remove both those and the remaining CCD and the remaining background light structure when we used additional round of median filtering. And at the end, you're left with what are, by image abstraction standards, very nice, great science-ready images. Once we have that, we're able to start doing some really cool science. So this is the main data from the paper I led earlier this year, looking at 20 bright events, where here, for us, bright is peaking at or a little bit brighter than 18th magnitude in TESS band. We had 20 events from the first 2 years of TESS operations. The bulk of these, as expected, is a pretty normal breakdown, what we would think we should see in a sample of Korkov supernovae. The bulk of our sample is the regular type 2 supernovae, and then a few of the CSM interacting type 2Ns, and then sort of the zoo of various 1BC subtypes. So to help characterize our light curves, what we fit was the power law you could see in red on all these plots. This is a 2-component power law. We're trying to be sort of agnostic in how we fit it. So we have 2 components so that you can fit the initial rise and then start turning over as you reach towards maximum light. Now, once we successfully were able to go and characterize the light curves like that, the first thing we wanted to go check was to see if there was an analog to the Phillips relation. So the Phillips relation is a known feature of type 1a light curves where how quickly they evolve is tightly related to how bright they get, and it's part of what makes them such excellent standard candles. So once we were armed with these exquisite TESS light curves, we had hoped to be able to go see a similar feature for these type 2 light curves, and maybe have another calibrator on the distance ladder to help resolve some of the issues that are ongoing among cosmology in the moment. But as you can see here, there's not a lot of blindingly obvious features or correlations going on here. Certainly in the darker points show some theoretical models I'll talk about in a minute. And they seem a little tightly correlated, but the real data doesn't seem too tightly correlated in any of these, except for maybe rise time and this second component power law index, maybe a little bit. Maybe you can squint and see something here between the first power law index and the absolute magnitude, but it certainly got quite a bit of scatter on a relation if it's there. And at this level of a sample size, it's difficult to say for sure that there is anything there at all. So this is certainly something we're going to need to collect more data on in the future to fill in, find if there's anything convincing here, and if there's anything practical for use outside of just saying that a relation barely exists moving forward. We went and compared to a suite of synthetic models calculated by Morozova et al. Back in 2016. So this work used over 100 models evolved through the Kepler and Mesa stellar evolution codes, and then exploded them by just injecting energy into the center and looking at the results in simulated ejecta and seeing what the light curves looked like. We took their data, converted it into synthetic TESS data, and then compared to our real data. So the one most important aspect of these models that I'm going to focus on is, you can see here in the lower right panel. So what we found, and it was consistent with what Morozova had noted in G-band, synthetic G-band observations, is that the rise time of the light curve, so the time from when it first starts brightening to its peak light, is very, very tightly correlated to the pre-explosion radius of the star, the size of the star right before it explodes. And this is consistent through both of the two different stellar evolution codes they use, through the various energies they use in their explosions. And we were able to get this calibrating line for test data, and we apply that relation to all the stars in our sample, all the light curves we had. We were able to get this fit here, or this distribution here on the right. So if you look, the black histogram shows all the red supergiants in our sample, and the gray histogram is the population of galactic red supergiants measured by Levesque et al. Back in 2005. So you can see this is very reasonable, and not only are the bulk properties reasonable, it peaks at around 640, 650, very reasonable standard value for red supergiant size. The distribution itself looks quite similar to that of what we are able to observe directly. So this is really, by itself, not super empowering. It's, added to the pile of reasons that we know core collapse supernovae of the standard type 2 variety are coming from red supergiants. But moving forward, especially, TESS should be this long duration mission where we should get years and years of data to help fill in this sample. And as it goes, what we hope to see is that it can fill in places where, or at least the ideal goal will be that as we go, we're able to fill in spots on here and see where supernovae, or where the high mass stars actually aren't exploding as supernovae. Because there's a whole ongoing exploration of theoretical space where there should be islands of explodability, what they're called, and islands of non-explodability, where you have stars of certain masses and certain radiuses shouldn't be able to explode. These are going to be the ones that directly collapse to black holes. And it'd be cool to be able to map that out with TESS if we can get sufficient resolution on this, which is, I think, an open question that I'm not immediately sure we have, and also sufficient, large N, basically. So stay tuned. That should be an interesting project moving forward. And the last thing I want to talk about a little bit is that we might have seen shock breakout, or hints of shock breakout. The shock breakout is just when the supernovae first begins. The first signature you'll get is as the shock reaches the surface of the star, it superheats the surface of the star for a very brief, 30 minutes or so, basically the light crossing time of the star. You get this flash, a very brief thing that you almost never get to see from the ground, but something like TESS with its essentially constant observations should be sensitive to. So we might have seen this, but we don't know for sure. Basically, you have this early time X, as you can see here in the panel on the right. This gray region is statistically significant, but it's not, it's not obvious that it has to be shock breakout. It might just be additional structure beyond the model we were fitting to this data. Certainly going to need to wait and get more events, and maybe ideally a really single bright event to help narrow down specifically what this might be. But interesting, certainly a good thing to stay tuned for. And as long as TESS keeps operating, I think it should be a really great platform for transient science. In particular, as I've talked about here, filling in that progenitor size distributions, particularly looking for these islands of explodability, I think is going to be a really great use, a very great science case for TESS. And also, if we run for a while, we're bound to get lucky again and get a really nice, bright individual. That's an 18 TB, which we can study in depth. And ideally, if it's a core collapse where we can go probe that early time region, see, we can figure out if it's shock breakout, if it's something, some interesting interaction with CSM. Lots of fun stuff going on there. So stay tuned.
Okay, thank you very much for that. Do we have any questions? If so, again, please put them into the Slack channel. And just give you a minute there. Okay, I don't see anything. So if you do have any questions as the meeting continues, again, please put them in the Slack channel. The next talk we have is by Jason Hinkle. I'll stop sharing my screen now. 1 second. Okay. So yes, the next talk we're going to be having is by Jason Hinkle. This is a test view of ambiguous nuclear transients. Over to you.
All right, can everyone hear me and see my screen?
Yeah.
Yes. All right, great. Thanks so much, Rebecca. I'm excited to talk today about ambiguous nuclear transients and especially how TESS fits in well with these in not only helping us to classify them, but beginning to understand the underlying physics. So in particular today, I'd like to talk about two nuclear transients that were discovered by the All-Sky Automated Survey for Supernovae, or ASSASSIN, and these objects are ASSASSIN 18EL and ASSASSIN 20HX. But before I get too deep into anything, I know most of you are primarily interested in studying stars and the exoplanets that orbit them, but as we talked about a little bit so far today, stars also give us incredible insight into transient astrophysics, in particular if they result in a total disruption event like this. They're excellent probes of supermassive black hole physics, which tell us not only about accretion and small-scale compact object physics, but have incredible importance both on the evolution of galaxies and when they're actively accreting galactic habitability. So throughout the talk today, I'm going to talk about two major classes of transients that we've hit on a little bit already, especially in Michael's talk. The first I've talked about a little bit here are tidal disruption events. Essentially, you have the violent death of a star when it gets ripped apart by a supermassive black hole, results in a luminous flare that can give us lots of information on the black hole and accretion. Typically, this is a bit of a higher accretion rate, and this is in contrast to active galactic nuclei, or AGNs, where you have a supermassive black hole at the center, but a somewhat more quasi-static accretion disk here that is a little bit slower in terms of feeding the black hole. But these are both incredibly important, not only to understand the physics of accretion and the environments of supermassive black holes, but to really understand the full range of behaviors that are happening in galactic nuclei. So before I really get into any of my individual objects, I just wanted to give you a little bit more sense of how TESS allows us to study these, just in terms, but nature is not always so kind to us in terms of having these two classes. Some of the events cannot be as neatly classified, and we call these ambiguous nuclear transients, or ANTs. And I hope I'll convince you today that it's the high photometric precision of TESS and the cadence that really gives us this unprecedented insight that's unavailable to us from the ground to really study these ambiguous objects and start to place them into these two classes even better. So as I said, I'd like to give you a little bit of a context just from the start where TESS fits in. If we're looking at a TDE in this case, as Michael already showed us, the TDE is ASSASSIN 19BT, we see that the TESS light curve is very smooth. Prior to the flare, we see almost no variability, and then during the flare, we see a very smooth rise to peak, and essentially no variability on top of this continuum shape. This, however, is quite different than the light curve of an AGN, which essentially lacks this broader continuum shape, and instead is characterized primarily by the stochastic variability. And this indeed is a key discriminator in nuclear transients, as we'll return to later in this talk. But TESS obviously is not only good for qualitative studies of these transients. We want detailed physics. We want to understand what is driving these transients in the first place. And that's where one of these relationships that I'll come back to later in my talk comes in great detail. So what I'm showing here on the y-axis is the characteristic timescale of variability in an active galactic nucleus as compared to the central supermassive black hole mass on the x-axis here. As you can see, there's a nice correlation that holds over several orders of magnitude in the black hole mass, all the way from the high mass quasars from this earlier sample of Kelly et al. Shown in blue, to this dwarf AGN NGC 4395 from Burke et al., which we'll hear much more about in about half an hour. But as you can see, what we hope to study here is really the trend in accretion that happens over many orders of magnitude to understand not only the accretion in an individual object, but in terms of a class of objects, what kind of similarities are there any outliers, and basically putting together a full picture of this accretion in black holes over many orders of magnitude. But as you can see, there's a region of this diagram where essentially we have no objects. And that's largely in part due to the fact that ground-based surveys simply don't have the cadence or the precision to get detailed light curves of these low mass black holes. And that's exactly where TESS fits in, essentially unlocking the key to the variability here on the very lowest mass black holes. So now that I've given a little bit of context, I'd like to jump into my first object, the ambiguous nuclear transient ASSASSIN 18EL. This actually happened in a known AGN, a narrow line or Seaford-2 AGN, but the transient itself was characterized by a slow, smooth photometric light curve in the optical band shown here, as well as the UV. which, as I mentioned previously, is usually typical of a TDE. In addition to having this bright luminous transient in the optical, there was the appearance of broad lines, characteristic. This is an example of what's called a changing look AGN, essentially going from these narrow emission lines at early times to much broader emission lines near the peak. However, though, this is not exclusive to AGN. TDEs are also characterized by broad emission lines, and this remains an ambiguous characteristic of this transient. And then finally, associated with these broad emission lines in the optical peak was the drop, an extreme drop in X-ray flux, which has been argued to be the disappearance of the X-ray corona in an AGN, and again has been argued in the literature to be the result of a TDE. However, this is not the full picture. We're fortunate to have TESS data on this object. But before we even get to that, I'd like to show the full optical light curve showing the later time data here, which will really be important in a second, because as you'll see, if we want to study the variability of this object, we obviously need much higher cadence than ground-based surveys can give us here. And in fact, this even required a little bit of stacking to get solid detections at the latest time. But as you can see, if we put TESS on this plot, we immediately get incredible precision and incredible cadence, much, much better than we could ever hope to do from the ground. And this allows us to really start to study the variability of this object in great detail. And that's what I've done here, essentially using a well-known AGN model to fit the late time emission of Assassin 18EL. And if you recall the earlier TESS light curves I've shown, this is clearly an example of that second case of high stochastic variability without any very general continuum shape. So this is fully consistent with an AGN picture for Assassin 18EL here. And if you remember that diagram I showed earlier, if we take this time scale of this variability, which in this case happens to be about 50 days, and then the black hole mass of this AGN, we find that it agrees incredibly well with this known relationship shown here. And again, this suggests that Assassin 18EL is consistent with an AGN. And as we continue to populate this diagram, not only with known AGN, but these ambiguous nuclear transients, we can hope to kind of shake out which of these may be consistent with this picture of an AGN accretion disk. So in summary, Assassin 18EL is no longer ambiguous. It appears to be an example of an AGN flare, albeit a very rare one, since it is, in fact, it has a smooth light curve. So Assassin 18EL, although it may be an AGN, is suggestive, or excuse me, pushes the boundaries of models for AGN flares. And we'll return to that point a little bit later. But now I'd like to shift gears a little bit and talk about the other anti-MI sample, Assassin 20HX. So right off the bat, Assassin 20HX was an extremely strange transient in that its spectra look unlike any known source class of transient. So what I'm showing here in black is the spectrum of Assassin 20HX, and essentially all it is a blue continuum without any clear lines. In particular, there's no emission lines, which would be strange for any nuclear transient. As I'll show here, in TDEs, we commonly see broad lines of hydrogen and helium. In superluminous supernovae, we see these lines of oxygen in absorption. And then in AGN, we see strong lines of hydrogen, as well as narrow forbidden lines. And as you can see, Assassin 20HX has none of these. And thus, from the spectra alone, we were clearly looking at something that did not fit well into any known source class and was therefore ambiguous. It's even worse if we look at the photometric evolution in that it, again, does not seem to fit into any known class of transient, being qualitatively similar to both TDEs and AGN flares, remaining ambiguous. But again, we're lucky that the host galaxy of Assassin 20HX was in the northern TESS continuous viewing zone in year 2 and allowed us to get incredible information both prior to the flare and at the very beginning. So looking at this quiescence period, we see that there are no flares brighter than about 19.5 magnitude, or especially clear that there's no flares even close to the level of the Assassin 20HX transient. And if we take this variability, we can make actually an even stronger statement about whether or not this is consistent with an AGN by computing a rough limit on the Eddington ratio. And the Eddington ratio here is essentially the ratio between the observed luminosity of an AGN and the maximum luminosity you can get out from accretion onto a black hole. Essentially, it's telling you how efficiently are you accreting onto the system, and tells you, in some cases, depending on what the Eddington ratio is, what the structure of the accretion may look like and what the actual physics are behind the observed emission. So if we take the red part of this light curve in quiescence and we compute a limit, you see that it's well below this sample of SDSS AGN, in fact, 4 sigma below. However, if we compare it to our own Milky Way's black hole, Sagittarius A star, it's well off the left of this plot, roughly 5 orders of magnitude below this limit. And Sagittarius A star has been argued in some cases to be a very low luminosity AGN. So this fact, along with the fact that during the flare, Assassin 20HX was similar to a median or normal AGN, suggests that maybe Assassin 20HX is just an example of a particularly dramatic AGN flare. Now, instead, if we just look at the flare part, we can compute a rise slope, which tells us about what might be powering the transient. And we find here a linear rise, which has only been seen in one other transient, Assassin 14KO, which Anna will talk about in the next talk. But interestingly enough, we are lacking theory in terms of any theoretical predictions in terms of rise slopes for transients. Some TDs have shown a quadratic rise. This is now the second transient to show a linear rise. But without any theory, it's not particularly clear what we should be seeing. And in fact, with only roughly 5 objects with any measured rise slope, it's not clear if we are seeing the same thing over and over again, or if we've just happened to find a few that look similar. So we really need to build the full context here. So again, without any theory to compare to, this is pretty unclear and remains ambiguous. So unlike Assassin 18AL, Assassin 20HX may be the antiest ant of them all and remains ambiguous, especially when adding test data to the picture. So far I've talked about 2 of these objects in great detail, and hopefully I've convinced you that it's pretty unclear where we are in terms of ants and the range of properties of nuclear transients. But what we really need to do more is to find more, especially with surveys like Assassin finding them. We can then use test data at almost any phase in the variability or any phase in the evolution to understand whether or not there is variability. And this is where the current TESS extended mission and future extended missions will be crucial to building a sample of ants to study. And I see that I'm running low on time, so I just want to move on to my summary and really impress upon you one final time that it's really the precision and cadence of TESS that allows us to study ants, not only to see if there is variability in the light curves, but when there is variability, to study that in great detail and to begin to pull out some of the physics in these objects and hopefully start to put together a more cohesive picture. And with that, I'm happy to take any questions. Thank you.
Thank you very much. Okay, I have a question in the chat. It's great talk, Jason. Could these ants be an intermediate state for changing look AGN?
That's a really great question. I think that it's possible that for some changing look AGN, well, I guess I should say that in the past, many changing look AGN have been discovered by spectroscopic surveys like the Sloan Digital Sky Survey, where essentially over many years, at a very low cadence, the galaxies were, spectra was taken of galaxies, and over time you'd see that lines change from broad to narrow or vice versa. So it's possible that now with ground-based surveys, finding things on much shorter cadences, that some of these objects may be an example of kind of an intermediate state. But again, with Assassin 20HX, even if that's a favorite explanation, you would still have to find a way to explain the fact that there is no emission lines. So I think that while that could be part of the picture, I think we're clearly seeing even more exotic behaviors from some of these objects.
Thank you very much. Any more questions in the chat, please? Okay, if not, thank you very much to our speaker again, and then we'll move on to our next talk. Okay, so our next talk is going to be given by Anna Payne. She is actually online, but I'm going to be playing the talk for her remotely. Is that correct, Anna?
Yes, thank you.
Okay, that's wonderful. One moment whilst I share my screen. Okay.
Hello, everyone. My name is Anna Payne, and I'm a graduate student at the Institute for Astronomy at the University of Hawaii. And today I am very excited to discuss my recent work on the discovery that Assassin 14KO undergoes periodic flares, which we currently think are most likely caused by a repeating tidal disruption event. There is a myriad of different types of transient objects, as we've been hearing about during this session, and black holes and their surrounding environment at the centers of distant galaxies are another prevalent source of transient phenomena. If we take a look at any normal AGN light curve, it is typically characterized by this stochastic behavior. Now, as Jason gave a great introduction to, this variability is by itself extremely interesting and is giving us information about accretion physics around the central black hole. But light curves from nuclear transients can also show large flares that reach amplitudes much greater than the baseline that are a signature of tidal disruption events. And these events occur when an unlucky star that's on a parabolic orbit has a close encounter with a black hole. The tidal forces overwhelm the star's self-gravity and it becomes torn apart and destroyed. The result is this luminous flare as some stellar material is forming an accretion disk around the black hole, and the remainder is ejected outwards in this stream-like formation. And because the star is completely destroyed in the process, this is a singular event characterized by one single flare in the light curve that gradually fades over time. What about the case of a grazing or near miss encounter? This is also the case of a partial TDE, and this happens when a star survives the encounter because the star is on an orbit with the pericenter outside the tidal radius, and the star is not completely destroyed, losing only a fraction of its total mass. And this case has been theoretically predicted for years and would result in periodic flares if the orbit of the star is bound and highly eccentric, but have previously been observationally elusive compared to total TDEs, of which now there are dozens that have been discovered. But light curves showing repeating flares have been reported before. The very first observational claim of a repeating partial TDE candidate was from an AGN back in 2015, based on the long-term X-ray luminosity light curve from Rosat, Chandra, and Swift observations, which showed these large amplitude brightenings about 9 years apart. And the partial TDE claim is rooted in the light curve showing indications of these repeated flares, but this light curve is sparse, and the behavior was not matched in other wavelengths. And a separate study associated these flares with extreme processes in the AGN accretion disk and not from the TDE instead. Completely opposite from 9 years between flares, X-ray light curves every 9 hours was recently detected from a different galaxy. These flares are clearly detected with high cadence data from XM Newton and Chandra, and one interpretation of the system is a white dwarf being tidally stripped in a highly elliptic orbit that completes one cycle every 9 hours. But again, in the literature, there are other possible origins that have been applied to the system, including oscillations due to the AGN accretion disk instability or interactions due to a black hole binary system. But regardless, both of these objects are considerably different compared to the object that I've been studying, which is Assassin 14KO. And last year, when I was starting the early stages of my thesis work and looking through a sample of AGN that were observed by the Assassin survey, this light curve immediately stood out. As opposed to the stochastic variation that is characteristic of AGN, there are evenly spaced flares that have been detected for the entire duration of the Assassin data, which now is spanning 7 years. And there are missing flares due only to seasonal gaps in the light curve. And I've been calling this object Assassin 14KO because one early flare was detected in 2014 with the Assassin transient detection pipeline and identified. But at that time, it was actually thought to be a possible supernova very close to the nucleus. But now looking back on the subsequent years worth of data, these flares are not a one-time occurrence, but instead are recurring events. And when I first found this object, the first question immediately became, are these flares truly periodic? And I found that using a mean period led to significant residuals in the observed minus calculated flare peak timings. And in fact, the timings of all of the observed peaks were fit much better with a timing model that included a period derivative. So in general, these flares show a mean period of about 114 days, but with a negative but non-zero period derivative. And as I'll talk about shortly, the TESS data provided a notable constraint given its high photometric precision and high cadence to the timing model. And the strong periodic behavior is very apparent when stacking the assassin data of the individual flares according to this timing model. There is a rapid rise in brightness followed by a decline, with each event lasting only about 40 days. And here I'm showing each flare separated by a different shade of blue. And I'm only showing G-band here for clarity but despite spanning 3 years of data, the flares have remained very consistent over time. So seeing the regular flares makes sense in the context of a TDE because we expect to see periodic flares if a star is on an elliptical stable orbit, with each flare corresponding to the star's closest approach. And because these flares are so strongly periodic, this gives us a really unique opportunity to predict when upcoming flares will occur. And May 2020 was the first time that a flare occurred as predicted using our timing model. I requested Swift data to monitor its evolution, which revealed for the first time that these flares brighten in near unison in the UV as well as the optical. And this picture came into even clearer focus in subsequent flares, which we again correctly predicted that happened in September 2020, again in December 2020, as well as April 2021. And even in the UV, these flares evolved remarkably consistent with each other. The UV bright evolution and UV bright emission apparent from the Swift data is very similar to what has been previously seen in other TDEs. And not only are we lucky in that these flares are periodic, so we can study them over and over again, but we're also lucky because of TESS. And I did know that there were TESS observations of this galaxy during sectors 3 to 5, because I was specifically gathering a sample of AGN observed by both Assassin and TESS. But I did not know until plotting this light curve just how perfectly TESS captured one complete flare very early on in the primary mission. The combination of TESS's photometric precision and cadence brought into focus this dramatic, sudden rise lasting only 5 days, and then followed by this gradual decline after reaching peak brightness. And TESS's extended mission further advanced this story. This galaxy was again in TESS's field of view during sectors 31 to 33, and again was timed just right to capture a subsequent flare. And note here that the scatter is noticeably larger because of the 10-minute cadence observations compared to the primary mission's 30-minute cadence observations. But because TESS viewed 2 different flares, we are now in a position to compare flare evolution in a highly detailed manner. In both cases, despite being 2 years apart, the flares evolved in a very smooth manner with very little small-scale variability superimposed on top of the flare itself, which is similar to TDE evolution and is not expected to occur due to AGN variability. And TESS is so crucial here because this was not unambiguous with just the ground-based data alone, given the level of scatter in Assassin. And this is very apparent by comparing Assassin 14KO to Assassin 19BT, which was the first TDE observed by TESS. Just like in Assassin 19BT, Assassin 14KO had no small-scale variability. But note here, there is a big difference in the timescales. 19BT declined over more than 100 days versus the very rapid event of Assassin 14KO encompassing only about 45 days. But regardless, the shapes are strikingly similar when shrinking Assassin 19BT to match the timescale of Assassin 14KO. But as I mentioned before, the fact that TESS observed 2 flares allows us to compare individual flare events and how they evolved through time. If we zoom in on the rise, in December 2020, that flare started its rise earlier, but rose slower compared to the November 2018 flare, taking longer to rise to a fainter peak. And I found that the rises are fit very well by the curved power law that was introduced by Patrick Vallely in his work on modeling the TESS light curves of supernova. And a similar trend was apparent if we take a look in a zoom-in view of the decline, where in December 2020, the flare had a flatter, slower decline that I found was bested by an exponential model. And these slight differences as observed by the TESS fits into the overall picture of interpreting Assassin 14KO as a repeating partial TDE, because they suggest these slight perturbations in the orbit of the star as it's being disrupted. Because keep in mind that even though the orbit is stable, as evidenced by the very clear repeating behavior, it can't keep going on forever in this perfect manner as it loses mass over each passage. So where does this leave us? This is where we're currently at, but Assassin 14KO is still going strong. And based on its behavior of as seen in the light curve will be populated by more events in the future. TESS provided crucial information about Assassin 14KO during the primary mission as well as the extended mission. And based on the current trend we see in the periodicity, future flares coinciding with future TESS data would likely be captured again. So Assassin 14KO is not just a unique object, but it's also forgiving in that it is repeatedly giving us more opportunities to study it. And I am very excited to see what its future holds. Thank you.
Okay, thank you very much. Do we have any questions? If so, please write them in the Slack. Okay, we have one question. Awesome talk, Anna. Assassin 14KO is such a fascinating transient. Do you have a prediction from when we'll stop seeing these repeating flares?
Thanks. Yeah, that's a really good question. So keep in mind that, we know that there are 7 years of data, but that was just when the Assassin survey started. So we have no idea when these flares started, whether it was 10 years ago or 100 years ago. But just considering the period derivative, it would go to zero at about 600 cycles. So that would be about 200 years, assuming that it just started. But, again, we know we have no constraint on when they started. So it could be, decades before we see any slowing down.
Okay, thank you very much. Do we have any additional questions? And also apologies, the meowing is my cat in the background. So. The cat's name is Aria. Thank you. Okay, well, thank you very much. Let's thank our speaker again, and we'll move on to the final talk for the day. That's going to be given, I believe, by Colin Burke. Colin's going to give his talk live, and it's about the optical variability of the dwarf AGN NGC 4395 from TESS. Thank you very much.
All right, thank you. All right, hopefully that's showing up okay. Thank you to the good. Okay, thanks. Thank you to the organizers again, and to the previous speakers. Really enjoyed those talks. So I'm Colin Burke. I'm a graduate student at the University of Illinois at Urbana-Champaign. And today I'm going to talk to you about our work on AGN variability, and specifically NGC 4395. My collaborators there, also want to acknowledge them at the bottom. So NGC 4395, why is it interesting? Well, it is one of the archetypal dwarf AGNs. That is an active galactic nucleus in a dwarf galaxy. So it's a dwarf galaxy, in other words, with a tiny supermassive black hole in the middle. We don't know the mass of it precisely. There's some papers out there that disagree a little, but I think we can say with a reasonable level of certainty that its black hole mass is around 10 to the 4 to 10 to the 5 solar masses. So one of the smallest known supermassive black holes, right on the borderline of what you would start to consider intermediate mass black hole. So here's an image of TESS and a ground-based image. So it's a big bright galaxy still resolved in TESS. So its Vmag is like 11, a little fainter in infrared. And yeah, as I mentioned, it's a well-studied dwarf AGN. And it's also been known anecdotally to have variability on a really rapid timescale and to be consistently varying with a high enough amplitude that you can get a nice light curve even in just a couple nights. So I figured this would be an excellent target for TESS. So once it was observed, I downloaded the FFI light curves, and we processed these in a similar way to the previous work using a difference imaging pipeline, which removes some of the base level background and trends in the images. We were a little bit lucky that this particular camera and CCD was not affected severely by scattered light or say a nearby bright star or something like that. And you can see there's those pesky charge straps, time varying straps along the columns here. Thankfully, those didn't interfere with the nucleus. So we were able to just mask those out, and they didn't end up being a problem. So the blue here is our aperture. We selected it by hand using the light curve tools. And the red stars here are isolated stars that were bright enough, and we got a good PSF subtraction for, which we'll use as comparison stars since they're nearby to the nucleus, but and use those to detrend the light curve further, because after the difference imaging, there's still some residual trends here. And just for reference, in the difference image on the right, the black circles there are variable stars. So the variability in this source is a little hard to see from here. I have an animation, which I don't think I'll have time to show here, where you can see it kind of flickering in the middle there. So we're pretty sure the variability is real and confined to the nucleus there. And when we extracted the light curve, I was happy to see that indeed we do see AGN-like stochastic variability. So that's the blue light curve there. And the comparison stars are shown in red. You can see there is still some residual systematic, some common trends in all of the comparison light curves due to scattered light. And there's some sections here which are kind of messed up due to the rolling band noise. But we were able to fit a model shown in gray here to capture those common systematics, which is just a spline model. And we fixed the shape of the model between all the stars and the AGN, and allowed the stretch to vary to account for different levels of the systematics that might be present depending on the aperture effects and so on. And when you subtract that out, you get quite a nice light curve here, and the comparison stars have small, basically are consistent with just no systematic trends in them. So after that, we were able to move on to the science for this object. So on the right here is the light curve, TESS light curve of NGC 4395 from before, which is previously shown in blue. And we fit a model here, which is now shown with a blue ellipse, called a damped random walk, which is a common model of AGN variability. And while there are some issues with the damped random walk, it's quite a useful model in the sense that it is easy to interpret and fits. We found that it fit our data quite well. We tried using a higher order model called a karma model. And we found that the fit was almost identical. So there wasn't a huge improvement using a more complicated model. And so the benefit of this damped random walk model is it has this characteristic time scale. And you can think of that as where the power spectrum flattens from red noise to white noise on long time scales. And the variability power starts to dampen. And so, which kind of makes sense if you think about it, there's some stochastic variation, but on long enough time scales, the AGN sort of has a relatively stationary brightness. And this is the plot that was shown before now with the relation between this characteristic time scale or the damping time scale tau in days versus the black hole mass. And here we have the previous data mainly from Macho observations of AGNs from Kelly et al. 2009. And I was really happy to see that 4395 falls almost exactly on this relation, with the caveat that its black hole mass is maybe a little uncertain. But considering the large uncertainty in the relation and the limited dynamic range of the previous work, really between 10 to the 8 and 10 to the 9 solar masses for black hole, that's more of a typical AGN or quasar. The uncertainty is quite large. So, and there were some previous or some follow-up papers that sort of called into question this relation, because it turns out you need to have long enough light curves and high enough quality light curves to be sure that you've measured the time scale appropriately to be statistically sound measurement. So our question is there really a relation between the black hole mass and this characteristic time scale? And if so, how can we interpret it? So after using our TESS light curve, which is great for studying the lower mass supermassive black holes with this very rapid variability on the timescale days, we also remeasured this relation, which are the black data points here, using SCSS quasars, more typical Seaford galaxies, and supplementing a few dwarf AGNs. So this isn't test data here. This is composite light curves from ground-based surveys like SCSS, Dark Energy Survey, and ZTF. And so this is work that's currently in press and science. And we can see that we've confirmed there is a relation that holds quite nicely across the entire range of supermassive black holes, including NGC 4395. And just for comparison, in red, I've shown the X-ray relation. So there's been some work in X-ray light curves showing a relation between the timescale and mass using X-ray light curves, and the variability in X-rays is, as you can see, on much smaller timescales, and the slope is also different. So we think this rules out simple models of X-ray reprocessing to explain the optical variability in these AGNs, and we think it's consistent with the thermal timescale at the UV emitting radius in the accretion disk. So in other words, we think this optical variability is something that's intrinsic to the accretion disk itself, because this correlation with the black hole mass is there. It seems to be robust, and the relation is different from the X-ray emission. So to kind of interpret this a little bit further, we compared this to the radius of accretion disk measurements using microlensing observations. So the microlensing constraint here is shown in blue from Morgan et al. 2018. And when you use the standard accretion disk model, essentially the Keplerian radius, which corresponds, so you can think of it as a characteristic radius, which corresponds to the characteristic time scale that we're looking at in the accretion disk. And without going into the details, if you assume that that radius corresponds to the UV emitting radius, then it's quite consistent with our relation is quite consistent with the microlensing data in blue within 1 sigma. And our relation probes the entire mass range of supermassive black holes, whereas microlensing in the previous work was really focused on the more massive quasars between 10 to the 8 and 10 to the 9 solar masses. So with these shorter timescale surveys, we're really able to, in higher quality data, we're really able to measure this with unprecedented precision. And also point out that we think this is consistent with the thermal timescale, and we're able to put a loose constraint on the viscosity parameter alpha in the standard model of accretion disks, which sets the normalization of this plot. But regardless, the correlation and the slope are consistent with microlensing. Finally, we said, well, why stop there? Let's look at white dwarf light curves, optical light curves of nova-like white dwarfs. And so this comes from Scarghini 2015. And those are the magenta points here at the bottom near 1 solar mass. And what we found is that the damping time scale in the optical of the nova-like white dwarfs is consistent with our relation in supermassive black holes within 2 sigma, and consistent with a slope a little bit steeper than ours of 1/2, which is the blue dotted, blue dashed line rather here. And so we think that slight inconsistency can be explained by a slight sample selection bias, perhaps in our data, which could be perhaps improved with future TESS observations at short time scale, and as well longer time scale observations of the most massive AGNs, which have characteristic time scales in this region of the plot on time scales of hundreds of days. So we think this could potentially be quite exciting if it hints that this relation is not only probing the accretion disk in AGNs, but could be universal across all accretion disks, at least that are rapidly accreting. And in between here is, of course, the missing link of intermediate mass black holes below our TESS NGC 4395 and above more massive than stellar mass black holes or white dwarfs. And so we hope that this relation could be used as a novel tool to enable intermediate mass black hole discovery, potentially with TESS or with other surveys which can probe the variability on the timescale of hours to days. And so thanks to TESS, we're able to show this relation here. And with that, I think I'll end there. And thank you for your time, and happy to take any questions or follow up later as well. Thanks.
Okay, thank you so much for your talk. Really appreciate it. We have a question from Michael Fausnaugh. Can you define the thermal timescale in more detail? Is it the same as the viscous timescale? I saw you derived alpha is 0.05. Sorry if I misinterpreted this.
Yes, correct. So this might be a little better to follow up afterwards, but yeah, so it's different than the viscous timescale. We didn't plot the viscous timescale on here. So I'd have to check where that would fall, but we think it's more consistent with the thermal timescale. This value of alpha is a little higher than what people usually assume, but apparently it is consistent with some MHD simulation of accretion disks. So as far as I know, there aren't great constraints on this alpha parameter, but yeah, something to follow up with in the future.
Thank you very much. I have another question from Chris. Any high mass supermassive black holes in the continuous viewing zone?
Yeah, I'm sure there are. I haven't looked. I think there will be a poster by a different group who's looking at that with TESS. So I'm excited to view that poster, and perhaps they'll have more to say than me.
Thank you. Next question from Thorendu. Great work, Colin. Can you also place the characteristic timescales of stellar mass black holes on that relation?
Great question. So I would refer to the Scarghini paper, which was published in Science Advances. We think we can, but it's a little more uncertain because the variability there could be contaminated by X-ray reprocessing. And if the variability is partly coming from stellar emission as well, it gets a little more uncertain. So I haven't looked into it in the optical in detail, just because we think it's a little more complicated in terms of actually extracting the right time scale that would correspond to the accretion disk variability and not something else.
Thank you very much. And the next question is from Emily. Hi, Colin. Could protostellar accretion be expected to follow the same relation, or is that accretion too slow? What if they're all in elevated accretion states, i.e. FU Ori bursts?
Yeah, so I think the question is about like young stellar objects. And so if I interpreted that correctly, it's not my area, but there was in this Scarini paper one young stellar object but that they were able to place on a similar relation. And that did seem to indicate that it would, assuming it's, accreting rapidly enough, that it would fall roughly on this relation, but there was only one data point. So I think it warrants a lot of future investigation. There could also be another scaling here that the questions are kind of getting at with respect to, is there a dependence on the accretion rate or the Eddington luminosity ratio in AGNs? And the answer is maybe, but with AGNs, at least in our sample, they don't span a wide range of accretion rates. So we found a pretty tight correlation, and we weren't really able to see if there's a trend or not with accretion rate. But that, I think, is really going to be exciting to look at with TESS and with stellar mass accretion disks, where you have more of a range of accretion rates, and that could really help nail this down. But we don't know yet.
Okay, well, thank you very much, everybody, for all of your talks. They've all been wonderful. If you have any more questions, you can please put them in the Slack channel, and our speakers will get to them as soon as possible. And I believe that's it for the talks for this session.
Rebecca?
Yeah.
There are a few things I wanted to say before we completely adjourn. And sorry I masked. But, I'm at MIT, and these are the MIT guidelines. I want to quickly show or briefly give you a run through the Gathertown space, in case you are less familiar with it. So I will share my screen. So Gathertown is probably the newest or least familiar online tool we are using. So not like Zoom or Slack, which everyone know. And so when you click on the link to Gathertown, you will get something that looks like this. It might show you a quick introduction, but eventually you get to this screen where you can, this is your avatar, and you can edit it a bit. You can change the appearance, overall appearance, and yeah, let's make something not too crazy. And closing, and eventually you can also put your name here and affiliation and so on. Click on next. You can turn on your microphone or your camera, but that might be confusing. So I'm now also on Zoom, and join the gathering. And actually this, I need to go to the main room. Yeah, this is where you'll enter once you click join the gathering. This is the main room, the main room of the Gathertown space. You can see many people walking around. As they approach me, I can start to see their video, and I also would start hearing them if my microphone was open in Gathertown. And you can also see the list of everyone here on the left. So right now, for example, there are 65 people here, including myself. If I wanted to talk to someone, I would click on their name. I want to find someone I know so I don't harass them. Oh, you. So you can click on someone, you can message them and directly. You can even go and locate them on the map. So this is me, and Osborne is now on the roof. So if I follow this route, I will get to him. So you can spy on people. There are many things here, and you should just go in and explore it yourself. But one of the primary things is that there are poster holes. There are 1, 2, 3, up to 9 poster holes. The entrance to you can see the entrance are here and here. In each of those 9 poster holes, there are up to 24 posters. So every poster has a hole and also a poster number within that hole. Now you might wonder, how do you know where the posters are located? So you walk up to these 1, 2, or 3 boards or podiums. You click on the X. You do need to wait a few seconds, and maybe a few seconds more, but eventually it will show up. It always shows up. There it is. And here you have the list of all the posters in the conference. It's quite a long list. There are like roughly 190 of them. And the first column here is the room number, point, poster number. So poster ID 3.21 is in hall number 3, poster 21. So, and you click on the, oh, I did not mean to do that. Okay, all the problems in presenting in real time. You click escape, and you get out of that, back to the main room, and then you can just walk into one of the poster halls. Let's click on this one. You walk up to this, click on the X. Here is the poster by Nolan Greaves. So this is about low mass stars. I think I'm on this paper, so I know it. Sometimes you need to scroll down here because not the entire poster will appear like this in one shot on your screen. And then you can go to the next poster and so on. So these are the posters. Other things we have here is we have like fun stuff. You go to the beach and you can hear the waves. Not sure if you can hear them over Zoom, but I can hear them. And there is a piano here which you can actually play. It's interactive, and there is like a video game like Tetris here that is all interactive and you can play. And inside there is also a roof area with, if you're cold, you can sit next to that campfire, get a bit warm. And so that's the roof area. There is also a TOI help desk area here, which is staffed by people from the TOI team. You can see that Chelsea is here now. So this is for answering any and all questions you have about TOIs. There is also a TOI help desk channel on Slack, which is exactly for the same thing. One last thing, if you want to hold like a meeting with a few people, there is these breakout rooms, 2 of them, and there is a board here. Click on the X, and there is a board you can, someone did not clean up after them, so we will clean it up, and we can make our own mess. And as long as you remember to clean up after you. Let's get out of this. And there is another breakout room down here. I think I covered everything. And yeah, that's basically it. If you have any ideas of what you want to see in this space, just let us know and we will try to add it. I should give credit to James or Jim Davenport. He's basically the person who made all this happen, almost single-handedly. So if you have any question, if you want to use Gathertown for your own group meeting or conference, he's probably the most experienced person with Gathertown to ask about that. Okay, so now we can go to the poster session. We blocked 1 hour in the schedule starting now for the poster session. I encourage everyone to go and explore the posters and also find colleagues you haven't seen for a long while, even if they walk down the hall, because nobody's been to the office for so long. If you see a poster that you like and you have any questions, you can try and find the lead author of the poster on the list of people here. And if you find them, like I showed you before, you can click on them and walk up to them and ask questions virtually face-to-face. I think this is it. I hope I got you excited about Gathertown. It was a bit weird for me like a month ago when I started using it, but I am now completely hooked, and this is the next evolutionary step in online meetings. At least that's my take on this. So I will let you go and explore. And so this is blocked for 1 hour. And the next session will be tomorrow, at least for most of us, depending on your time zone, it is tomorrow, starting at 9 a.m. East Coast time or 1 p.m. UT. And see you all next time. I will stop sharing, and we can end this session. Thank you very much. Thank you for Rebecca for sharing, and for the speakers for being on time.